Good afternoon, everyone, and welcome to our PTV Talks session for today. We have a presentation from David Florence, who is from Texas A&M Transportation Institute. He will be describing the simulation environments created using PTV Vissim for the traffic optimization for Signalized Corridors small-scale test and evaluation project. Just a couple of items before we get started. We will be having a Q&A session at the end of the presentation. You can enter your questions in the questions box anytime throughout the presentation, and we will answer as many as possible. A recording of today's webinar will be posted to ptvtraffic.us in the next day under the Resources tab. A link will go out to you in a follow-up email tomorrow as well. Please make sure while you are on the website that you take a look at the Resources tab to catch up on any webinars you may have missed. With that, I will give it to David.
Great. Thank you, Liz. So like Liz said, I am David Florence with the Texas A&M Transportation Institute. I'm going to be talking about a project that CAMP invited us to join them with. CAMP stands for the Crash Avoidance Metrics Partnership. It was in particular the Vehicle to Infrastructure Consortium, represented by the 8 auto manufacturer groups shown on the screen here, that invited TTI, UC Riverside, and UMTRI to assist them in developing this system. This project is federally funded. It's funded by FHWA. Here's the number for it. And here's a disclaimer to show, or to state that the opinions, findings, and conclusions don't necessarily reflect those of US DOT. So today I'm going to be talking about how we took TOSCO from a concept to an evaluation, a simulation evaluation on State Highway 105. To accomplish that goal, I'm going to go through and describe what TOSCO is. Again, that stands for Traffic Optimization for Signalized Corridors. I'm going to describe how TOSCO was developed using Vissim at a low-level vehicle development simulation, and then how we expanded TOSCO to allow us to assess the impacts through a traffic assessment simulation. I'll discuss some of the simulation challenges that we had along the way, the next steps for the project, and like Liz said, I'll take some questions at the end. So what is TOSCO? The first part of TOSCO, the part that enables these vehicles to behave the way they do, is the infrastructure. The infrastructure has an algorithm that takes the detection from the intersection and processes that data to produce queuing information that we pack into the SPAT message. It also uses signal controller data and data on how that intersection is operating to produce what we call the green window. The green window combines the queue information and the signal timing information to provide a recommendation to these TOSCO vehicles on when they can arrive at the intersection when there are no vehicles queued and the signal is green. This information is broadcast via roadside equipment, again through the SPAT message, the map message. RTCM messages provide correct GPS corrections to these vehicles so they're able to determine which lanes they're in. And these 3 messages are broadcast to the vehicle part of TOSCO. Now, vehicles equipped with TOSCO will hear these messages and use that data along with data coming from the vehicle's interface, the CAN interface about their speed and acceleration and so on, to control these TOSCO vehicles as they approach a signalized intersection. The TOSCO algorithm provides a 1-degree autonomous behavior. It controls their speed as they approach the intersection. The driver is still responsible for steering and maintaining their position in the lane. But what TOSCO does is that as the vehicle approaches the intersection, it will make decisions once it enters communication range to either speed up, slow down, maintain constant speed, or if unavoidable, come to a stop at the intersection. The next few slides will describe these options in more depth. So, as a vehicle is approaching the intersection, it has its set speed, that is the speed that the driver indicated that they prefer to travel. And once they enter communication range, they'll start receiving those messages I mentioned earlier, the SPAT, map, and RTCM GPS corrections. That information provides a speed limit for the vehicle, so it is able to determine its optimal approach to the intersection. It will decide which method to use once it enters communication range and attempts to follow its best profile that allows it to cross the stop bar as soon as possible. Now, if a stop is unavoidable, what the TOSCO vehicles will do is they will, of course, come to a stop. And as they begin to depart from the intersection, once it turns green and there are no vehicles queued in front of them, these TOSCO vehicles will perform what we call coordinated launch. This enables the vehicles to discharge that queue quicker, and any TOSCO vehicles next to each other will accelerate at close to the same time, behaving as a string of TOSCO vehicles. So the first option, the first operating mode that we have listed here is the speed up operating mode. With this, the conditions for this is if the driver's current set speed is below the speed limit, the TOSCO vehicle will determine that it will accelerate to the speed limit, maintain that speed, and go back to the set speed after it crosses the intersection. The mindset behind this TOSCO control strategy is it allows the vehicles behind the subject vehicle to cross the stop bar at a sooner point in time. The next TOSCO operating mode is the slow down operating mode. The conditions that lead to this decision for a TOSCO vehicle are such that the vehicle enters communication range and determines that it currently will not arrive within the green window. As depicted here, it's determining that the signal is currently red as it enters communication range, and it will turn green at some point in time, and it aims to arrive at the stop bar the moment the signal turns green to help and increase your number of vehicles that can go through that lane. Now, if a stop is imminent, the vehicle will, of course, come to a stop at the intersection. The vehicle will maintain constant speed as long as possible, such as not to produce some sort of safety hazard of vehicles approaching a slow-moving TOSCO vehicle. And the vehicles will come to a stop at the intersection, wait for the signal to turn green, and then perform its startup behavior, a coordinated launch. And like I said, a coordinated launch, if there are multiple TOSCO vehicles in a line, these TOSCO vehicles will begin departing at the same time. They will use gap control up to a certain speed and then start keeping a certain time gap between the subject TOSCO vehicle and the vehicle in front of it. The mindset behind coordinated launch is to increase the saturation flow rate, get more vehicles through that intersection in a certain amount of time than manually driven vehicles. So to develop TOSCO, we came up, to develop it and evaluate it, we came up with 3 different simulation environments. Today I'll discuss in depth 2 of these. I will discuss the vehicle level simulation environment, developed mainly by and other partners within the TOSCO team. I'll talk about the infrastructure I'll talk some about the infrastructure simulation environment that we use to develop these infrastructure algorithms that calculate some of that data necessary for TOSCO vehicles to approach an intersection. And I'll discuss in depth the performance assessment environment that we use to determine how TOSCO might impact State Highway 105, like I mentioned earlier. The first simulation environment that I'll discuss, is the vehicle level simulation environment. This environment represents TOSCO at a very low level. It represents how the radar on a vehicle would operate and the occlusion it would have between the lead vehicle and any vehicles around it. It represents DSRC communications and the BSM sit between vehicles. It represents, and most importantly, it operates TOSCO as if the algorithm thinks it's driving a real car. Now, to do all of that, it takes quite a bit of computational burden, and so we split this load across 3 different machines. The first machine on the far left, the development environment, is the machine that hosts TOSCO and operates the vehicle control as if TOSCO thinks it's operating a true real-world vehicle. This data is passed through the simulation environment, which hosts Simulink, and it processes data and translates information from the development environment to the traffic environment. Now, the traffic environment is where we have Vissim. It involves modeling the infrastructure component that enables TOSCO to behave the way it does, and it, of course, models the simulation of the vehicles and every time step as they go through. This environment enables us to represent TOSCO and develop TOSCO without needing vehicles on the real world. And it was a cyclic process and still remains a cyclic process to this day. We start off defining our simulation objective and specifying what we want to alter. We'll enter the parameters into the simulation, run some simulations, plot the results, document and figure out what happened in these, identify any changes that we need, and develop the software to support those changes. And we repeated this process over and over again throughout phase 1 of the project and continue to do it now that we're in phase 2, as we continue to refine the TOSCO algorithm and test it using Vissim and the other software in this environment that is repeatable and reliable. So the key findings and key results that we had out of the vehicle level simulation that we were able to refine the TOSCO system using this vehicle level simulation and ensure desirable behaviors in each operating mode. We had simulations that set up the vehicles such that they enter the network and produce the different operating modes that I listed earlier in the presentation. We'd have one model for constant or speed up scenario, one model for the coordinated stop scenario, and other models that represent, say, if the string of TOSCO vehicles needs to split and some vehicles pass the intersection and other vehicles perform a coordinated stop. We were able to refine these algorithms and determine that the initial speed profiles we started with TOSCO were actually insufficient because they didn't include initial acceleration. That was one of the main things we learned through the vehicle level simulation. As we tried to make our first set of speed profiles work and the governing behavior for TOSCO, we determined that we needed to refine them and include initial acceleration if we're going to make TOSCO work. Now that we're in phase 2 of this project, we're continuing to test the algorithm with the vehicle level simulation. We have the vehicles entering communication range, and we're changing the parameters and changing things up a little bit for these vehicles to further refine them without the cost and lack of repeatability we'd have in the field if we were to test these vehicles on a closed course. Now, the outputs from the vehicle level simulation enabled us to figure out how TOSCO would behave, which then fed into our development of the traffic level representation. Like I said, TTI represented State Highway 105. This is in Conroe, Texas. It's a little bit north of Houston along I-45. The corridor we selected to model TOSCO is a 15 intersection across 12 miles running east-west between Conroe and Montgomery. The posted speed limits on this facility range from 45 miles per hour on the east end to 55 miles per hour on the west end. And actually, 55 miles per hour covers the majority of the facility. Only about one intersection on the far east end of the corridor is at the 45 mile per hour speed limit. To analyze TOSCO, we simulated the AM and PM peak scenario. We did a 2-hour peak period for the 2 of these. And we went through various market penetration rates of TOSCO, 30, 60, and 100%. To get the traffic level environment to operate thousands of vehicles compared to the 5 vehicles represented in the vehicle level simulation, we needed to simplify TOSCO slightly. In the traffic level simulation, we don't represent, say, the radar and occlusion, but we use the driver model DLL API provided by Vissim to translate the gaps between the vehicles and other data necessary and represented by the radar and so on a real vehicle. our infrastructure algorithm uses the ASC3 virtual controller, like the vehicle level simulation, to take that signal phase and timing information and collect it for all 15 intersections so that it can send that information to the vehicles, to the simulated vehicles. The driver model DLL in the traffic level simulation environment hosts the TOSCO behavior. We took the TOSCO algorithm and simplified it such that it would operate thousands of vehicles thousands of vehicles at the same time, using the same TOSCO logic represented by the vehicle level simulation. This simulation we also utilize the emissions DLL API from Vissim so that we could calculate the emissions produced by TOSCO. Because one benefit that we foresaw of TOSCO is that it could perhaps change the amount of emissions generated by vehicles because vehicles are not coming to a stop as frequently. To operate State Highway 105, we need a little bit of information. We collected the signal timing plans provided by the city of Conroe, Texas, and we collected turning movement counts at each intersection so that we had the right inputs into the data for our respective time periods. We calibrated the simulation based on travel time studies, tube count locations, tube counts at 5 different locations along the facility, and we determined that we actually needed to calibrate the acceleration behavior. Now, why did we calibrate the acceleration behavior? Well, when we showed this plot to our auto manufacturer friends, they said the non-TOSCO vehicles are accelerating quite aggressive. To put that, the blue line on the right is the TOSCO behavior as the vehicle accelerates from a stop. And the red line on the left is the acceleration of the default behavior from Vissim vehicles. So we collected data to represent the true acceleration behavior of vehicles on State Highway 105 so that we could calibrate our model to more accurately represent the true acceleration behavior of vehicles on the facility. The reason this is of interest to us is because we're developing a vehicle system. We need to be able to draw a comparison between the baseline traffic representing human drivers to the TOSCO algorithm that changes the acceleration for the vehicles that are equipped. This, of course, the change in acceleration behavior led us to recalibrating the simulation compared to when we didn't have the calibrated acceleration profiles. And we analyzed TOSCO for select market penetration rates for the AM and PM peak scenario after we calibrated to the travel times, volumes, and the acceleration behavior. Now, this slide represents some of the setup and findings from our acceleration study. This could be an entire presentation of its own. In summary, the acceleration study, we took the default desired acceleration function represented by the plot on the upper right that has the distribution of acceleration for vehicles across speed as they accelerate from certain speeds up to their desired speed. Our 8.9 feet per second squared is a pretty aggressive acceleration, especially when you compare that to our findings of about 2.5 or about 3 feet per second squared from a stop from our vehicles that we represented on, say, Highway 105. We found this acceleration behavior using an accelerometer in some test vehicles that we took to State Highway 105. We attempted to imitate the acceleration behavior of vehicles ahead or beside of the vehicle that we had with an accelerometer, and we filtered the data so that we only had acceleration information of vehicles that were near the front of the queue so that they're not following somebody in front of them. So this reduced the likelihood of vehicle interaction editing the desired acceleration behavior, which is what we were trying to capture. And we smoothed the data and compressed all the acceleration profiles that we collected into these functions that I have graphed here in the bottom right. You can see some pretty big differences between the two. And one of the reasons that the lower graph seems to level out and then extend up to a very high speed of about 155 miles per hour is so that any vehicles that have a desired speed higher than 65 would be able to accelerate to their desired speed eventually, given that they have very low acceleration after the point of 65 miles per hour. This plot shows the differences. It has the same two lines as before. The red line is now a dot dash red line, and the blue line hasn't changed for the TOSCO behavior. We found that, and the new yellow dashed line is the manually driven behavior with the calibrated acceleration profile. You see that the TOSCO vehicles still accelerate slower than the non-TOSCO vehicles with the revised acceleration profile. But you also see that the revised behavior has the vehicles taking longer to accelerate up to their desired speed. And the revision of the acceleration behavior here shows acceleration that is more consistent with the literature on how vehicles accelerate from a stop. So some of the results that we have from the simulation are represented in this slide. This slide represents the total delay and stop delay of the AM peak simulation. It shows the eastbound and westbound direction. For this time of day, the eastbound direction is the peak direction. And you can see that the total delay increases as market penetration goes up and the stop delay decreases. Now, this isn't exactly a surprising result. We expected this to some degree in moderate traffic because TOSCO's main goal, TOSCO's main strategy for avoiding a stop at the intersection is to slow down and come to a speed such that they do not need to stop. And naturally, one could expect that slowing down leads to some increase in total delay. What you need to focus on for this graph is that the stop delay goes way down. We're talking it goes from close to 50 seconds all the way down to 10 or even 5 seconds for the westbound direction. And this shows that TOSCO is helping the vehicles remain in motion so that they are not spending a bunch of time queued at the intersection. Now, the PM peak simulation shows a slightly different story. Now, the PM peak has several intersections along the facility that are in a saturated condition, meaning that the queues never really clear. The signal timing does not allow all the vehicles to cross the stop bar. What we can see here is that for the eastbound direction, which remains the peak direction in the PM scenario, you can see that there is a drop in total delay between the 0% and the 30% market penetration rate. And then it actually sort of levels off after 30% market penetration. You can see that the stop delay remains on a decreasing trend with increased market penetration. And you can see even the westbound direction has some decreases in total delay for the PM peak scenario, given that this has much more traffic in the facility. We found that this is primarily because of the coordinated launch behavior of TOSCO vehicles. When TOSCO vehicles are able to accelerate faster, they're able to accelerate with less lost time. That is, they don't need a human to react to the vehicles in front of it as it accelerates, or as the vehicle in front of it begins to accelerate. And so coordinated launch enables TOSCO vehicles to clear that queue faster. Now, I was asked to show that this facility, or that an intersection was over capacity, which is actually one of the challenges. It's a challenge in Vissim because there's not exactly a way to show per se that something is over capacity and how it changed that way. So what we did to show the capacity improvements is we honed in on the queue at a certain intersection. This intersection is near the middle of the facility. This represents the eastbound traffic. Now, we took the graph, we graphed the baseline represented by the blue line here. And you can see that at the beginning of the analysis period, we had a warm-up period at the beginning of the simulation. You can see that the queue is already quite long, and it continues to build, and the queue remains high up until about halfway into the simulation, when the traffic starts to decrease and it's no longer rush hour. You can see that the other three market penetration rates, the 30%, 60%, and 100%, remain at near zero queues. And so this indicates to us that adding TOSCO to the vehicle stream in an overcapacity scenario can help that increase your capacity such that there is no longer a repeated queue at that intersection. So in conclusion, in light traffic represented by the AM peak scenario, TOSCO is able to reduce stop delay, number of stops, but it increases total delay. Now, TOSCO vehicles experience this higher total delay because they currently accelerate slower than baseline traffic and will slow to the speed limit if necessary while in communication range of an intersection. One of the things that we're looking at in phase 2 of this project that is ongoing is what sort of acceleration parameters can we provide to TOSCO such that is more consistent with how with the accelerations recorded on State Highway 105. How can we allow TOSCO to accelerate faster and perhaps see more benefit of the TOSCO system? Now, in heavy traffic, TOSCO is able to reduce total delay, stop delay, and number of stops. The increases in capacity are from reduced headways in the TOSCO stream, and they're great enough to overcome the average increase in total delay by the TOSCO driving behavior. We didn't change behavior between the AM and PM peak scenario. TOSCO's tool was still to slow at an intersection such that it can cross the stop bar during the green window. But when there's heavy traffic, there's not really a green window for those TOSCO vehicles. And so we know that it is the coordinated launch behavior that is the reduced time and reduced time to startup and the reduced headway between vehicles. That enabled TOSCO to increase capacity at one of our intersections and to reduce the total delay. These modeling results indicated enough positive benefits to begin moving forward and start doing some field testing in phase 2 of the project. We're still doing simulation, but phase 2 involves actually building the TOSCO system and testing it on a facility and a couple facilities, as you'll see. Now, some of the challenges that we had in the TOSCO simulation was getting all the different software and different computers to talk to each other in a synchronized fashion. The synchronization between multiple machines for the vehicle level simulation and different pieces of software in the traffic level simulation proved to be a challenge. We had to get the software to wait and listen to hear bytes from another piece of software or another computer so that TOSCO could operate like it will in the real world. We had to compare the TOSCO behavior to the baseline traffic. Like I discussed, our acceleration was very important. The input acceleration for that baseline traffic proved to be very important for the comparison of TOSCO, which is unique to developing a system and a low-level vehicle behavior using Vissim. We had to collect unique performance measures, such as operating mode. That is, what kind of did they choose to speed up? Did they do a coordinated stop? Did the vehicles perform a coordinated launch? We built code to help record these operating modes in the simulation. And we had to record speed trajectories, like I showed several of here, to describe how the vehicle started up from a stop. And we had to record signs of oversaturation and somehow quantify it beyond level of service F. We wanted to show when and how was oversaturation produced, and when the intersection was no longer oversaturated. In phase 2, we have, what we're doing is we're refining these algorithms further. Like I said, we're entering these TOSCO vehicles with different entry times, with different parameters, such as higher acceleration, higher maximum acceleration, and playing around with those parameters. We're building TOSCO such that it will operate at the TTI Relish campus. We have runways, and you can see it pictured here. We have an operational test intersection that has all the components that we need to perform TOSCO behavior. And we'll be able to do this on a closed course and develop TOSCO further. We'll conduct verification testing on this facility and verify that the real vehicles are able to perform as TOSCO is, as we expect, and as TOSCO should. We're going to integrate any refinements to the TOSCO vehicle logic into our traffic level simulation so that we can rerun this and see how did our refinements impact State Highway 105. And given funding from FHWA, we plan to deploy this system on State Highway 105 and see and run TOSCO vehicles through the live intersections along the facility so that we can further refine the system and prove that TOSCO is able to operate and improve the behavior and improve the performance on State Highway 105. So I know I went through these a little bit fast. It looks like I have plenty of time remaining, and I'd be happy to accept questions.
All right, thank you very much, David. If anyone has questions, you can enter them now in the questions box, and we'll try to take a few questions here. Was there any thought about using any kind of real controllers, like a hardware in the loop or anything like that, or are you leaving that for the next phase of testing?
We are working with hardware in the loop simulation now as we are developing the infrastructure algorithms to operate outside of the simulation environment. But for simulation, we had an advantage in using a software controller. Using the soft controller, we're able to run it faster than real time. Because when you're using a real controller, it is only ever able to operate at real time. It doesn't understand the idea of simulating a time faster than the current clock speed. So we were able to run the simulation at faster than real time using the software controller within the traffic level environment. For our vehicle level environment, operating those 5 vehicles went slower than real time, but it was a much more complicated simulation. That's a good question. Thank you.
Okay, and for the actual field deployment, what's your plan as far as communication technology at the intersections? 5G, DSRC, what were you looking to do?
Right, this project is a DSRC project. We plan on using DSRC. Given that the changes in the FCC, which is probably part of this question, we're now looking at doing all of our communication through channel 180, which is untouched by the proposed changes by the FCC.
Okay. Excellent. So what are your thoughts on some ways to improve, once you go past the 30% penetration rate, you start to see a little bit of a decline in the savings, delay savings. What do you think could be done to maybe help boost those at higher penetration rates?
That's a good question. Well, I think one of the things that will help TOSCO is when we start tweaking with the parameters and playing around with how TOSCO behaves. So far, phase 1 was mostly proof of concept. We wanted to see and evaluate how TOSCO would operate on the facility, in particular our high-speed facility, which is unique to this type of system. Most other tests of an approach and departure vehicle control algorithm were performed on a low-speed facility. But for our high-speed facility, we wanted to see how it would behave kind of as with our first cut. You can see that we already refined the speed profiles for TOSCO and such that it would operate. And in phase 2, we plan on looking at all of these and looking at the different parameters that perhaps could help us improve as we increase market penetration better than what we saw in phase 1. So we could change the acceleration behavior, the maximum accelerations for TOSCO. We could say reduce time gap for TOSCO and other settings involved with how the vehicles behave.
Okay. A couple questions came in as well in relation to signal timings. How much, if any, consideration was given to tweaking those signal timings to take advantage of this behavior, or have you considered looking at some kind of, something like an adaptive system or something like that that would could take advantage of knowing that those vehicles are there?
That's a good question. We have that listed as a possibility for TOSCO, but currently we are not pursuing changing in signal timing. Part of that is that we don't want to try to change too many things at once. We want to be able to analyze these impacts separately. And another part of that is that we don't really want to ask too much of the city of Conroe. They're already generous enough to let us, prepare this system for their facility and eventually deploy it on their facility, given funding. But we're currently not looking at changing the signal timing or using any sort of adaptive system because we want to evaluate TOSCO itself.
Okay, great. Just a couple more things and maybe some couple questions more related to like nuts and bolts type things within Vissim. For example, for queues, were you collecting those through the nodes or with queue counters? What was your method for doing that?
Right. So when we set up this evaluation, we use nodes around every intersection. And so those plots were created using the node results for the through movement, eastbound through movement at one of our intersections. Part of that was that we didn't have a queue counter at the intersection, but we found that node results were able to collect reliably many different performance measures. So we didn't actually need a queue counter at that intersection to produce this data. We, of course, had to change the time interval so that we could graph it across the analysis period, or we had to ensure that the time interval was low enough to graph it across the analysis period. But we were able to produce that graph using node results.
Okay. For the emissions piece, can you describe a little bit how you implement the emissions model, DLL, or what underlying methodology we're using to generate that information?
Yeah. The emissions model DLL actually behaves quite similar to the driver model DLL in my experience. It sends data to the C++ interface during simulation, and it provides certain pieces of data that we were able to utilize. So it provided, for example, the acceleration in the vehicle type, so we knew if it was a truck or, say, a passenger vehicle. We could even tell if it was a TOSCO vehicle. And we were able to utilize the acceleration, vehicle type. I think there's even an option to use the slope and produce our own code to represent the emissions. So we use the moves model to represent emissions on the facility. And this required us coding in the different bins and the logic that produces emissions based off moves. One nice thing that the emissions model DLL was able to do for us is it was able to send emissions data back into Vissim. We were able to read it directly within Vissim. Now, it doesn't send it back into all locations, and I actually don't remember which exact locations it sends to, but it's all in the manual. So the emissions model DLL allowed us to use our own code to represent the moves algorithm. And so you could use something other than moves with the emissions DLL if that's an important part of your project.
Okay, one other kind of interesting question here. Did you look at anything based on the spacing between intersections? Is there was any difference between closely spaced intersections versus intersections that were further apart, whether that made a difference in the results?
Right, yeah, that's a good question. We do have various spacings between the intersections. We did find that since the facility has different timing plans and it has coordination between intersections, those intersections that were closely spaced to each other really didn't benefit much from the TOSCO behavior because there was good progression between the two intersections. If you left one intersection going eastbound, you were likely to get a green indication at the next intersection going eastbound. Whereas the intersections that had larger spacing between them, we observed via animation more changes in TOSCO, or that TOSCO was able to change the acceleration behavior with more knowledge than, say, the manually driven vehicles. Now we're in phase 2. We plan on producing some simulations to look into that a little bit further. So currently it's an observation that we have from the animations and such. But that's a great question, and we did look into it some, but we didn't build any analysis about it yet.
Okay. I think one other interesting topic is safety. Through like SSAM or some other methodology, did you evaluate if there was any impact on the safety along the corridor?
So we did humor the idea of looking into safety. Now, safety remains one of the big challenges for modeling behavior in any micro simulation, right? Because the vehicles sometimes don't necessarily behave the way you know that they would in the real world. So currently, we have not used SSAM with this analysis. We did the idea of using some sort of enter during red or something like that for the analysis, but ultimately concluded that that isn't necessarily a safety impact. Now, of course, running red lights isn't a good idea, and the TOSCO vehicles don't, but it doesn't necessarily mean that there was a crash, right? So we humored the idea some, but currently there is a large amount of data produced by this simulation, and we didn't look into producing the large trajectory files used by SSAM.
Okay, I think with that, we're going to go ahead and conclude the question and answer portion. I really appreciate everybody joining us today, and a special thanks to David for taking the time to give us this presentation today. Just so you know, if you missed anything today or came in late, we are going to be sending out an email tomorrow that's going to have a recording. So make sure you check that out and pass it along to anyone who might be interested. As well, we have a couple other webinars coming up in the near future. The next one's going to be on March 12th. It's going to highlight the Coexist project, which also talks about modeling autonomous vehicles. We've done some other webinars regarding this project. So we want to take a time to kind of sum up some of the information as well as incorporate the latest results. Following that, on March 19th, we are going to be doing another tooltip session. Similar to the one we just concluded, where we're going to be discussing the scenario manager in Vissim, parking lot creator, as well as modeling some flared approaches. So make sure to watch out and sign up for that if you have not already. Once again, thank you everybody for attending. We really appreciate you being a part of this series, and we hope it proves to be very useful for you. David, once again, thank you very much, and everyone have a great day.